This is about limit laws and theorems from section 2.3. And so before you start watching this video, you should make sure that you can reference the handout that I sent. One of them is a worksheet that you will be filling out. The other one is a reference sheet that basically has the limit laws on it that I'm going to be referring to a lot. So you should have that reference handy so when I refer to it, you know what I'm talking about. That would be the best way. So if you need to stop this and go put it up on your screen so you can look at it, do whatever you need to do. Okay, so limit laws and theorems. This is the handout that I sent you guys that I want you to be looking at. It gives us a bunch of limit laws that have been proven, so we can use them. And so it says this: suppose that c is a constant, and that the limit as x goes to a of f of x and the limit as x goes to a of g of x exist. Then we can say all these things. And so they give you I listed basically 11 rules that we can use. So it makes it nice. Number one says the limit as x goes to a of f of x plus g of x is equal to the limit of f of x plus the limit of g of x. And so in words, the first rule says the limit of sum is the sum of limits. What that means is, right here, the limit of sums is the sum of limits. Look at A right here. We're going to do this one, but we're going to apply that rule. What that basically means is that the limit as x goes to 2 of f of x plus g of x, the limit as x goes to 2 exists for both of these, and so we'll be using that in a minute, means that we can apply that law. So we can look at this as the limit as x goes to 2 of f of x plus the limit as x goes to 2 of g of x. The limit of sums is the sum of limits. That is what the first rule says. The second rule says the limit as x goes to a of f of x minus g of x is equal to the limit as x goes to a of f of x minus the limit of x as x goes to a of, sorry, let me start over. The limit as x goes to a of f of x minus g of x is equal to the limit as x goes to a of f of x minus the limit as x goes to a of g of x. In other words, number 2 says the limit of a difference, the subtraction of two things, is the difference of limits. So this is basically, if we look at B, which is a problem we'll be doing in a minute, we have right here the limit as x goes to 0 of f of x minus g of x. By law number 2, the limit of a difference is the difference of limits. This is equal to the limit as x goes to 0 of f of x minus the limit as x goes to 0 of g of x. The limit of a difference is the difference of limits. That's what that one says. Then we have another law that says basically the limit as x goes to a of c times f of x is equal to c times the limit as x goes to a of f of x. That, number 3, basically means that if you have a constant multiplied times a function, a number, a real number, a constant, multiplied times a function, you can just move that constant in front, multiply that, and then take the limit of the function. So I don't have one of those, but basically that law says, like if I had 3 times the limit as x goes to 2 of f of x, if I had the limit as x goes to 2 of 3 times f of x, this is equal to 3 times the limit as x goes to 2 of f of x. So you can take this constant and move it in the front as a factor right there. That's what number 3 says. Number 4 says if you're taking the limit of two things being multiplied, you can split that into two limits being multiplied. In words, number 4 says the limit of a product is the product of limits. We do have one like that in C. So this is the limit of a product. This is equal to the product of limits. The limit as x goes to -1 of f of x times the limit as x goes to -1 of g of x. That is what that law says right there. D is limit law number 5. If we're looking at D, this is a quotient. Number 5 says the limit as x goes to a of f of x over g of x. This quotient is equal to the limit as x goes to a of the numerator over the limit as x goes to a of the denominator, provided that the limit as x goes to a of the denominator does not equal to 0. So we're not allowed to divide by 0. And if that happens, then the limit doesn't exist. So that is the condition when you're doing the quotient. So this is equivalent to the limit as x goes to 3 of f of x over the limit as x goes to 3 of g of x, provided that this does not equal to 0. That's the condition there. All right, E, oh, we'll get to that in a second. Then 6 is another limit law, which is if you're taking the limit of a function being raised to a power, then you can put the limit inside that and then raise it to a power. Number 7, the limit of a constant as x goes to a constant is just that constant. So if I have the limit as x goes to 7 of 21, this is equal to 21. See, there's no x in this function. Nothing's going to affect the fact that the value of this constant function is 21. There's no x. This could be x goes to 100, negative 1,000. It doesn't matter. This is still going to be 21. So the limit of a constant is just the constant. And so then we have the limit as x goes to a is just a. And there's a few other little rules that you should look at. Right now I want to get on with the theorem that we have. Here, this is the first one we're going to start with, direct substitution. Direct substitution says this: if f is a function and the function f is either a polynomial or a rational function, which a rational function is the division of two polynomials, and a, the number is in the domain of a, is in the domain of the function f, then the limit as x goes to a of f of x is the same thing as if you substituted in a right there. So how can you find the limit of a function when it is a polynomial or a rational function? You just substitute in that value right there. So we're going to hang on to that rule and use it as we go along. So that's one I wanted to introduce. So now I'm going to erase some of this extra stuff off, and we're going to go to the worksheet, which you're going to be filling out as we go, and these will be on there. I have copied over the graphs right there that were on your worksheet for you to see. So let me erase some of this stuff. The direct substitution, I wanted to introduce that one, and I have, and so I may refer to it, and that's just where you can substitute in the value of a when you're evaluating a limit. Okay, so to the worksheet that I gave you guys for you to work on, it is called Practicing Using the Limit Laws. We are going to use these graphs to find out what the limit of the function is at different values. So, this is what they ask us to find. The limit as x goes to 2 of f of x plus g of x. I already applied the limit law that said I could use that as the limit as x goes to 2 of f of x plus the limit as x goes to 2 of g of x. What you're going to do is use these graphs, and we've already discussed how to evaluate limits. I'm just going to do a couple of these and you'll see how it's going to go. The first one, for instance, look at your graph. The limit as x goes to 2. All right, so where is 2 on your graph? 2 is right here. This is 1 and this is 2. Okay, so the limit as x goes to 2 from the left and from the right looks like it's headed to negative 1. So the limit as x goes to 2 of f of x is negative 1 plus, what is the limit as x goes to 2 of g of x? So here's the graph for g of x. From the left and from the right, it looks like it's headed to the same point, and it looks like it's going to be 2. So negative 1 plus 2 is 1. That is the answer for part A right there. You're going to go through and do the same things for each of these. Let's do D real quick. The limit as x goes to 3 of f of x. So here we are, f of x. Where is 3? Oh, I didn't label my x-axis, so that's problematic. Let me find it. 1, 2, 3 is about right here. This is 3. And so if I go up there to 3, 1, 2, 3, it is continuous right there. And so it's this point right here. And so from the left side of 3 and from the right side of 3, it's headed to this y value, which is the number 1. And so the limit as x goes to 3 of f of x is 1. Okay. Let's go to g of x. Here is 1, here's 2, here is 3. The limit as x goes to 3 of g of x, from the left it looks like it's hitting this point. From the right it looks like it's hitting this point. So it's going to be this point. What is that y value? This y value is the x-axis. It's 0. Oh, but this is the one condition that says I'm not allowed to apply this rule. So really does not exist is the answer to that one right there. That was the condition that that would keep you from being able to use that rule. Okay, I'm going to show you how you would do F, and then we'll come back and do E together. f of negative 1. Do you see the word limit here? No, not at all. This is what you knew a long time ago, well before you ever thought about taking calculus. How do you evaluate a function at a value? So graphically, go to the f graph. Here it is. This is saying, what is the y value when x is negative 1? Well, when x is negative 1, I am here. Where is it defined to be? This is open circle. It is not defined there. This is the closed circle. It is defined there, and so 3 is the answer to that. F of negative 1 is 3, plus the limit as x goes to 1 of g of x. So this is a limit at x is 1. So at 1, we're going to go from the left, and we're going to go from the right, and I'm going to have to look at my little chart on g. And so 1, we have to do a little bit of guessing. It looks like it's going to be like 1.3 maybe. It's a little bit of a guess right there, but it's definitely, there is a limit that exists from the left, from the right. It's about right there. So maybe this is 1.3 is what I've decided that is. Maybe you thought it was 1.4, something like that. So this is going to be 4.3. That's how we'll do that. And we're going to come back to E. We're ready for E now. The limit of a product is the product of limits. So let's look at this. I can use that rule. Let me pull this out over here. So I can say this is equivalent to the limit as x goes to 2 of x squared times the limit as x goes to 2 of f of x. Just like we did for C. The limit of a product is the product of limits, provided that these limits exist. X squared is a polynomial. And so direct substitution is the theorem I'm going to use right here that says to figure out what the limit as x goes to 2. See, I don't have a graph, but it doesn't matter. This is a polynomial, which means I can use direct substitution. The limit as x goes to 2 of x squared is the same thing as just if I substituted 2 in for x and squared it. So that's going to be the limit of that because this is a polynomial. And then I'm going to multiply that times the limit as x goes to 2 of f of x. Over here, f of x. Here is 2. It's not even defined at 2, but that doesn't matter. We're looking at the limit. The limit is negative 1. And so we'll say times negative 1. 4 times negative 1 is negative 4. That's what the answer to E is going to be right there. All right, I'm going to leave the rest of those for you guys to put in there. I think that you'll just get practice reading graphs and plugging that stuff in. I'm going to move on to explain what the squeeze theorem is so we can apply it. So that's the next theorem we're going to be looking at. All right. So before we can actually apply the squeeze theorem, there is a theorem that we need building up to it. And this is a very great theorem. But before we can use it, there's this theorem that we're going to look at, which says, if you have a function f of x, and it is always less than or equal to g of x over some open interval that contains a. So that is off of the first worksheet where I said, refer to this. So if you, it's on the top at the back of oh, it's how I have it printed. It might be on sheet 2. It's on the top of the second sheet. And it says, theorem number 2 is what it's called. And it says, if f of x is less than or equal to g of x for all x in the open interval that contains a, except possibly at a, if f of x is less than or equal to g of x on some interval that contains, so this function is always lower than or equal to g of x, okay? If we look at this picture, which we're going to look at for a minute, let's just say we're looking at the interval from 0 to x. The purple graph g is always less than or equal to, is always greater than or equal to f. F is always lower than g. If we're looking on the interval from 0 to x, g is always, the purple graph is always lower than h. That's what that's saying right there. Outside here, do you see how this purple graph goes higher than the red? That's fine because that's outside of the interval from 0 to x. So that was not even in the interval. So as long as we have some interval where one graph is always lower than the other one, we can say this. Then the limit as x goes to a of f of x will either be less than or equal to the limit as x goes to a of g of x. Okay. All right, so that is one theorem that we can say. Now, here is the squeeze theorem, sometimes referred to as the sandwich theorem, because do you see how G is sandwiched or squeezed between graphs f and h, functions f and h? This is why it got that name. It simply says this: if g of x is squeezed between f of x and h of x near a, and f and h have the same limit L at a, then g is forced to have the same limit as a. So basically it says this: if the limit as x goes to a of f of x, right here, the limit as x gets close to a of f of x, it looks like it's approaching this point, which is L, and the limit as x goes to a of the upper function h is also that same value, L. Okay, when we get close to a, we look at h, it's also L. Then the function that's squeezed between those on that entire interval, the limit as x goes to a of g of x, is forced to have the same function L. If the outer functions that are containing the inner function have the same limit at that point, the inner function has to have that same limit value at that point. So that is the squeeze theorem, also called the sandwich theorem, also called the pinch theorem. So you might hear it in different ways. All right, here is an application of the squeeze theorem that we can use. They might say, go find this limit. So here is one. A lot of times they'll use it for trig functions, which is nice. If they say, show that the limit as x approaches 0 of x times the sine of 1 over x is equal to 0. Let's just say that's the truth, or we got to show that. Okay, how could we do that? Well, first, let's take out this trig function right here. What do we know about the sine and the cosine? It might have been a while since you've had trig, or maybe you just had it. I don't know what your situation is, but let me you recall a sine wave or a cosine wave. Here's a cosine wave. It starts high, goes low. Here's a sine wave. Starts at 0 and goes on like this. Okay. But if you recall the range of this sine wave, it's always going to be between 1 and -1. If you recall the range of a cosine wave, it is always going to be between 1 and -1. That is the truth. So if we say, what is a function that would bind the sine function, because it doesn't matter what the angle is, remember this is an angle, it doesn't matter what the angle is, the output of the sine of an angle will never be bigger than 1 and will never be less than -1. It's contained in there. Then we have a constant function or a horizontal line. -1 is always less than or equal to the sine of whatever, is always going to be less than or equal to the constant function y is 1. This is just the truth. That's the range of a sine function. Okay, well, since x if x is getting close to 0, x is some positive number. Let's call this, I wanted to change, can I do x or could I do x squared? Hang on just a second. I wrote that down. I wrote that down. We're going to do x squared. This is the one on your worksheet because this will make it very, very clear. We're going to change that to x squared. This is the one that you have to do for your worksheet. If we multiply all of these by x squared, then x squared is a positive number and it will not change the sign, the inequality value. So if you multiply it by a positive number, it will not change the inequality sign. So we're going to say, I'm going to multiply this by x squared. -1 times x squared is -x squared. Will be less than or equal to x squared times the sine of 1 over x will be less than or equal to x squared. This is also true. Then let's apply a limit. Let's take the limit right here. Let's take the limit as x goes to 0. The limit as x goes to 0 of this outer function, -x squared. Well, this is a polynomial, and by direct substitution, I'm allowed to substitute in 0. So 0 squared is 0. 0 times negative 1 is 0. So the limit as x goes to 0 of this is 0. Let's do the limit of this other side of the function. The limit as x goes to 0 of x squared is, okay, this is a polynomial. I'm also allowed to substitute in by direct substitution rule. Substitute in 0 for x. 0 squared is 0. This is equal to 0. So if the limit as x goes to 0 of this function is 0, so let's see, the limit as x goes to 0 of negative x squared is less than or equal to the limit as x goes to 0, the limit as x goes to 0 of x squared times the sine of 1 over x is less than or equal to the limit as x goes to 0 of x squared. That's just true. That's the first theorem I showed you. But if it turns out that the limit as this goes to 0 is just the number 0, and the limit as x goes to 0 of this is just the same number, 0. So in the squeeze theorem a minute ago when I did it, it was L, not 0. That's fine. But if it's the same number, this guy stuck in the middle is forced to have the same limit. So therefore, by the squeeze theorem, the limit as x goes to 0 of x squared times the sine of 1 over x is equal to 0, just like that. Okay, so that's an illustration of the squeeze theorem. Now, what is left to do is to do a few examples algebraically and to look at the greatest integer function. I'm going to stop this video and start a new one so that you can have a break.